Hello. Today we're going to talk about making predictions with linear models. So in order to do that, we're going to have this real-world situation. It says the National Weather Service uses a chart to determine the wind chill factor at various wind speeds. So, you've dealt with weather. Wind chill is the cooling effect caused by wind blowing on a surface. This phenomenon explains why you can feel colder on a windy day than on a calm day. Even if both days have the same air temperature, the following table shows the air temperature in degrees Fahrenheit and the corresponding wind chill factor for a wind speed of 20 miles per hour. Now, a lot of times when we're given something like this, we're given a set of data and they say find a regression. When you find a regression, that's the same thing as finding a line of best fit. It's basically taking your data, plotting it on a graph, and then finding the line, the straight line, potentially, that goes through that data the best. That way we can make predictions and figure out how to use that information to find out other things. So we are going to graph this data, and you have it on your paper in front of you. So I'm just going to come over here, and we're going to use Desmos. And I'm going to pretend that you've never seen Desmos in your entire life. So we come to desmos.com, you click on Calculator. To add a table, we're going to hit Add this item right here, and then put in a table. And we're going to type in our table the way we see it in our paper. Now, the X column is going to be the top row, and the Y column is going to be the bottom row. So we have 40, 30, 35, 24, 30, 17, 25, 11, 24, 15, negative 2. So it's getting kind of cold over there. Now, or it's feeling cold, right, if nothing else. And once you have your data in here and you're on Desmos, it should, we can't see these points because our graph is so far over. So in order to do that, you just scroll in, or you can use the zoom feature in Desmos, and now we can see all of our points. We're going to find the line of best fit here, and we're going to make it linear. So we're going to come over here to where it had those little buttons, and we're going to say linear regression. This right here, that's our linear regression. So now we can answer some questions and really figure out what this is getting at. So we're going to come back to our paper and we're going to write that equation down. So the equation for this regression is y equals 1.291x minus 21.514. And that tells us some things about this equation. The first thing it tells us, remember, y equals mx plus b, that's our standard form. So we've got y equals mx plus b. Remember, b is your y-intercept, and m is your slope. So when it asks what is the slope of the regression line, the slope is going to be this number right here that's in front of x. So the slope is 1.291. In this problem, this means, so let me write this out for you, that the wind chill factor increases because it's positive by about 1.291 degrees Fahrenheit for every 1 degree Fahrenheit increase in air temperature. Okay, so as your air gets colder, the wind chill factor gets even colder faster because 1.291 is bigger than just 1. What is the dependent variable axis intercept, and what does it mean in the context of this problem? Now, a dependent variable, that's your y-intercept, because your independent variable is your x. So your dependent variable is going to be where it touches the y-axis. And actually, we know what that is because in our equation, b is your y-intercept, which means that the intercept is the point 0, negative 21.514, because that comes from this number right there. And what does it mean in the context of this problem? Well, it means, so this means that if the air temperature is 0 degrees Fahrenheit, right? Because that's what the X value is there, with a wind speed of 20 miles per hour, the wind chill factor is negative 21.514 degrees Fahrenheit. All right, that's just really interpreting the point in the problem. Finally, in part D, we need to use the equation of the regression line to estimate the wind chill factor for a 32-degree day with a wind speed of 20 miles per hour, and show the work that leads to our answer. So what does that mean? Well, it's giving us the wind chill factor, and our equation is 1.291x minus 21.514, where your input is the air temperature, and the output is the wind chill factor. So if it's asking for a wind chill factor and it gives you a temperature, we're taking the temperature and we're plugging it into the equation. The wind speed of 20 miles an hour just means that it's the same equation, it's the same situation, right? Because the wind is moving out 20 miles per hour. So we're going to take 32 and plug it into our equation. So y is going to equal 1.291, and then we're plugging in 32, and subtracting 21.514 because that's the rest of the equation. Now when we do this math, we get 19.798. So the wind chill factor is 19.798 degrees Fahrenheit when the temperature is 32 degrees. That's it. Fairly painless.